Hello guys! Last week when I was ill, I wanted to talk about algorithms. So I created this video so we can talk of algorithms even though I was ill. So let's start by defining what is an algorithm, then classify them, and we'll look at some problems regarding it and some small exercises along the way. So first of all, what is an algorithm? So an algorithm is a set of steps that are followed in order to solve a mathematical problem or to complete a computer process. In our case, it's usually the last one. Algorithms can be deterministic, which is given a particular input, it will always produce the same output. This is quite easy to test. And usually an algorithm is like that, but there are non-deterministic algorithms. They are non-deterministic because they use, for example, randomness or external states. The algorithm does stuff depending on the content of the database, the weather, the temperature, the day of the week, or whatever, external states. So, we have here the friendship algorithm from Dr. Sheldon Cooper, PhD, which is, as we can see here, a series of steps to follow. An easier way, or more old-fashioned way to see an algorithm would be a baking recipe. If you do this and you do that and then you do this and then you do that, then you'll end up having some lovely cookies. Let's look at a computer-based example. So here we have an array with 3 numbers, and I have this method that checks if in A 8 exists. It's quite easy for us to see here that it doesn't. It will return false. And here, when we have some more numbers, it will return a true. So in this case, how long time will it take our algorithm to execute? So let's look at the algorithm down here. And it's easy to see that it will run through all the numbers if it's not there, and it will stop immediately if the number is present. Which means that the worst case complexity here is it will take longer time to execute when there are more numbers. Yeah, that wasn't hard to figure out, but how much more? If we have 3 numbers, it will look at 3 comparisons. So, this error, if we focus on that, we can see that if we have 3 numbers, we might run this line of code 3 times, and if we have 9 numbers, we might execute this line of code 9 times. So it is said that big O, which is the worst case time complexity, is equal to the amount of data. So we classify it in respect to how many times a certain line is executed, which means we look at the data amount and not the actual data. And we don't care for CPU speed either. We'll come into that later. So if we have here, which is a sorting algorithm, we take an array and we run through this array several times until the numbers are ordered. So what is the time complexity of this one? Yeah, we'll figure out by looking at this line, because this is the essential line. So up here we have a for loop that runs, if we got in data, it will run n-1, and this for loop is also n-1. So we could say that big O of n is n-1 times n-1, which means if we got 11 numbers in our array, we will loop through 10 numbers 10 times, 100. If we look at the math, a bit unclear here at the screen, but we can see how the math looks like. But we don't care for the -2n and the +1. These are small. We'll look into that later. We're saying that this particular sorting algorithm is big O of n to n squared. So there are different kinds of classifications. We can see here that we have n, which means the more data, the more time. We have log n, which means the more data, a little bit more time. And then we have the n squared and all the others on the left saying a bit more data, a lot more time. Let's dig a bit deeper into it, because it looks like we have 3 different kinds of algorithms, but we don't. So if we zoom in a little bit, we can see that we have different time complexities even here. And we can zoom in even more. So we have something here that says a little bit more data, a lot more work, or vast a lot more work. Why is it that we don't care for CPU speed? So here we have 3 different graphs, all saying n squared, but with a different constant on it. And we can see that they are rising in exactly the same amount. So this could very well be a slow CPU and a fast CPU. Or here we have a time constant. Yeah, they look the same. So we are only caring for the part of the formula that has the most value, n squared in this case. Usually we operate with these different time constraints, and big O of n equals 1 is very good. That means regardless of the amount of data, it will always take the same time. More usually is n or n squared. We have the fastest sorting algorithms is log 2 of n times n. There are problems though that we say cannot be solved on a computer. So if we look here, we have n squared and n to the 3rd and n to the 4th. And we can see that they become more and more difficult. But they are all what's called a polynomial, because they are squared with a constant number. So it could be n to the 5th or 6th. And we say everything that is faster than a certain polynomial is calculatable. So these are in polynomial time. Hard to say. And those up here, which could be a faculty, is said to be not polynomial time, it should have said. So in polynomial time we can calculate areas, we can encrypt stuff, and we can sort numbers, and lots of other algorithm types. But in the NP complexity problem we'll find stuff like Sudoku, or finding encryption keys. Usually encryption is by taking 2 primes and multiply them together. And if you want to break an encryption, you get this key that contains 2 primes, and you want to factor them out to get the original primes. This is an NP problem. And it's an NP problem because nobody has found an efficient algorithm to do that yet. But use a few seconds to think of what will happen if somebody came up with an algorithm that could take any number and factor it out in an efficient way, so we could get these prime numbers quite easily. For the example of efficiency in algorithms, I have found the Fibonacci number. So let's look at what is the Fibonacci number. It's an order of numbers that is shown here. You take the 2 prime previous numbers and add them together to get the current number. That can be said like this. So the Fibonacci of 0 is 0, Fibonacci of 1 is 1, and Fibonacci of numbers greater than 1 is calculated from like this, a smaller Fibonacci number. This is quite elegant. So we can actually rewrite this to C# in a very elegant way. So we just call the method itself And to look at the complexity, we could, if it should be easy, either look at how many times are the method calling itself, or we could simply just calculate the time or measure the time it takes to execute it. Measuring time is not as precise as measuring the amount of calls of a certain statement in our program, and that's because normal modern computers do other stuff than just calculating. They might do system stuff in the background, which takes time, sometimes takes time from the actual algorithm, and sometimes it doesn't. So measuring time is not as precise, but good enough for us. So I have looked at how much time does it take to calculate this Fibonacci, and the stuff in red is because I was impatient, so I just estimated it. There are some. This is following a quite simple algorithm, so you can calculate how much time it would take. And on my computer, Fibonacci of 70 would take approximately 175, 76 days, approximately. So what would happen if I, instead of having one CPU, had 16 core CPU? That would be neat. But it requires that this algorithm can be parallelized, and it can't. And even if it could be parallelized into 16 parallel running computations, it would still take me 11 days to calculate n of the 70. It's a lot of time. And that's why we don't care for all the small constants. We are only going for the vital. And this is 2 to the nth. We'll look at that later. But what if we could rewrite the algorithm instead to something like this? Then it would be linear time. Then we could, with less than a millisecond, calculate n of 70. So rewriting the algorithm has saved us a lot more time than just following the old algorithm. Now it's big O of n equals n. So why is the Fibonacci numbers, so why is the original Fibonacci calculator so slow? It's because Fibonacci of 4 is Fibonacci of 3 plus Fibonacci of 2. And Fibonacci of 3 is 2 plus 1. And Fibonacci of 2 is Fibonacci of 1 plus Fibonacci of 0. And Fibonacci of 2 is Fibonacci of 1 and Fibonacci of 0. And that we can calculate. That was 1, that was 0. So now we get 1, we get this, this, and this. So a lot of calculations in it. But worse is that, look at these two. They are totally alike. So think if I didn't want to show you Fibonacci of 4, but Fibonacci of 70. Then I would have a lot of equal calculations, a lot of things. This algorithm that I rewrote a few seconds ago, it's the fastest. But usually it's a bit difficult to rewrite recursive algorithms like that. So when you want to make a recursive algorithm more efficient, it's usually easier to do it like I've done here, to get some kind of knowledge base storage, in this case a dictionary, and then whenever we want to calculate something, we look at the dictionary to see if we have already done that, and if we have, we'll look at the dictionary instead, and if we don't have calculated it, then we'll calculate it and store the result in the knowledge base. This way we can always go back and look in the knowledge base. This is quite simple for the Fibonacci numbers, but we have other recursive algorithms in which this is very useful and time saving. So if we calculated something, why calculate it again and again? Think of a chessboard. If we calculated once, what will happen if you move this piece of whatever, if you move the king and the queen is still standing, and we look at some of the other stuff on the board, and we go back to save it and reuse it later. This is still in linear, so big O of n equals n. So I'll have the dictionary, and here I check, are my results already calculated in the dictionary? If not, calculate it and put it in the dictionary. So, as you can see, big O of n is way better than n 2 to the n. So, thanks for watching, and remember we have different problems here. So while the CPU is growing and growing, as you can see in my graph here, the amount of data is always growing faster. And it's not enough to have a lot of CPUs. We might use algorithms and look at the efficiency of algorithms instead.